Hello everyone and welcome back for our last chapter of the semester, chapter 17. So this chapter is called Radioactivity and Nuclear Chemistry. So what we're going to learn a little bit about is how radioactivity works, what it means for an atom to be radioactive. And this video will kind of take a tour through how radioactivity is associated with your everyday life and where you may have come in contact with it. So let's get started. Radioactive superheroes. Oh, I kind of look like I'm Spider-Man. Radioactive superheroes, right? That's one place where we've heard of this before. Peter Parker was bitten by a radioactive spider to become Spider-Man. Bruce Banner was bombarded with gamma rays to become the Incredible Hulk. But we're constantly experiencing radioactivity in our everyday lives. So, where's my superpowers? Dang it. So let's get into what radioactivity is so we can mourn our non-existent superpowers together. So, radioactivity is the emission of these tiny invisible particles by the nuclei of some atoms. These can be a few different kinds of particles that are emitted. We'll talk a little bit about that. And each kind of emitted particle has different properties and affects humans or living cells, for instance, in different ways. So atoms that emit these tiny invisible particles are said to be radioactive. So if something has this characteristic of radioactivity, it's said to be radioactive. So we use the properties of these particles in many ways in our everyday lives, and they can be harmful in some cases, don't get me wrong, but when we're careful and we know what we're doing, they can be extremely useful in many other ways. So, let's talk a little bit about three different types of radioactivity, of radiation. These are not all the different forms of radiation that are out there, but these are three that I think we could talk about that are kind of relatively easy to understand. You won't need to know specific information about the types of particles. However, you should know that these particles have properties called ionizing power and penetrating power. And you should know that there are different kinds of radiation and different kinds of particles that can be emitted. So just know that there are different kinds, but I am going to talk a little bit in detail about three different kinds that can be emitted. And again, there are more than just what we're covering in this class as well. So, alpha radiation is radiation that emits particles made up of 2 protons and 2 neutrons. So basically, a nucleus is some sort of unstable, and when it decides it's going to go through some sort of radiation emission, it gives up a proton or 2 protons and 2 neutrons, aka a helium atom, and it shoots that off. So when this happens, you're actually changing the identity of your original nucleus. So if you start with one thing and you change the number of protons, aka here we're emitting 2 protons, you're going to have a different identity of something else in the end. So alpha radiation, these are the largest particles that are emitted in radioactivity, and they are the best at messing things up. These are kind of like the big baddies that you don't really want to deal with. So they have a high level of what we call ionizing power. So they can easily ionize atoms and molecules. It's got 2 positive charges there, so that those 2 positive charges can easily affect something else trying to steal some electrons to balance its charge out, right? So they easily ionize atoms and molecules. So this can cause extreme damage to living cells by changing the interactions of atoms and molecules within those living cells, right? So if something is ionized and it was neutral before, it's not going to participate in the same kind of chemical reactions as we learned. So with this high level of ionizing power, alpha radiation is super dangerous. The catch is it has a very low level of penetrating power. Because these particles are relatively large in comparison to what we're going to talk about for other types of radiation, they actually have a hard time getting to the cells. So it's really easy to block alpha radiation. So we always think about all of this lead shielding, all of this concrete, all of this tough stuff. They built the sarcophagus around Chernobyl to contain all of the radiation, right? Well, they're kind of containing some other kinds of radiation doing that. However, Alpha radiation can literally be blocked by a sheet of paper, a cloth mask, clothing, because it's so large in comparison to the other things we're talking about. So while alpha radiation has the biggest potential to actually ionize cells and cause problems, they actually have a hard time getting to the cells to cause that problem. For example, you're going to hear a lot about my internship at the nuclear power plant in this chapter, but when we worked there, one of our main concerns was if we saw leaking water when we were walking through the plant. We always had to report it because it might contain some sort of radiation if it was leaking from the wrong place, and that meant that alpha particles might be exposed to us. And if you breathe in an alpha particle, well, then it's inside your lungs and inside your soft tissues and in your respiratory system, and that's going to cause a lot of problems with the living cells there. So you don't want to be breathing in something like this, which is why you could wear like a cloth or paper mask. However, most places where we were working in the plant, we're not really dealing with a lot of radiation. We'll talk about that later. But it was one of our main concerns, was making sure that we weren't exposing ourselves accidentally, specifically to alpha radiation, because it's so dangerous, but it can be very easily blocked. So another type of radiation that you might experience, or that exists, I should say, is called beta radiation. So it's radiation that occurs when a neutron is changed into a proton, and then that particle that is emitted is an electron. Subatomic particles, if we're following the quantum mechanical model of subatomic particles and using like quantum physics, all subatomic particles, protons, neutrons, and electrons, have the ability to transform into one another. Just accept what I'm saying. So a neutron can be changed into a proton, and then it's going to emit an electron when this happens. So this really only usually occurs in extremely unstable nuclei, and when this occurs, again, you're changing that identity of your original nucleus, right? So we have a neutron, it turns into a proton, so now we've changed our number of protons, changed the identity of our atom, and we've emitted an electron as our form of radiation. So the particle that's emitted here is an electron. So think about how much smaller that is than an alpha particle, right? So an alpha particle is made up of 2 protons and 2 neutrons. However, beta radiation, the particle that's emitted, is an electron. So it's much, much smaller, okay? So if we're thinking about these terms of ionizing power and penetrating power, beta radiation, or these beta particles, aka these electrons, they're not as large or as quote-unquote powerful as alpha particles. They fall somewhere in the middle of the list I'm making down the line here. So they have less ionizing power than alpha particles do. They're just an electron, so they have kind of an electron's amount of ionizing power, versus that 2 positive, we've just got a 1 negative here. However, they have a much higher level of penetrating power, right? So they're just electrons, so they're so much smaller than those alpha particles, as I mentioned. So this means they have a higher chance of actually getting to the living cells to manipulate them in the end. So even though they aren't as strong at that ionizing power, they can still do that, and they can still ionize things. So we need to kind of think about it that way. So they can kind of get to you more, even though they do less. So there's kind of like a game of numbers there in the end. This beta radiation with these beta particles, aka electrons, they can actually just be blocked by a sheet of metal. Metal loves to take in electrons, that's its favorite thing. Or like a thick block of wood or something like that. That should be enough to stop beta radiation in the end. So while it may do less to you, it's much harder to stop beta radiation from getting to you in the first place. Okay, let's talk about one last type of radiation here, and then we'll kind of sum up what this all means in the end. So the last thing I want to talk to you about is gamma radiation. So this is radiation given off as high energy, what we call photons. So these are like little particles of light. So when you have gamma radiation, and we're giving off gamma radiation, This kind of radiation doesn't necessarily change the identity of the particle at hand like the others do, right? So in alpha radiation and beta radiation, the number of protons in the end change. Often in gamma radiation, it's given off in conjunction with one of the other types of radiation in the end. So it's just kind of in combination with all of these things. So gamma radiation is the most likely to get to you because it's so much smaller, but it has a lower ionizing power. So what do I mean here? Well, gamma radiation is the smallest of particles because it's a light wave. It doesn't actually have any mass to it or charge to it or anything like that. So this means it has a high level of penetrating power. Gamma radiation is the hardest to stop. This is what we're thinking about with all of those thick several inches of lead shielding or those slabs and slabs of concrete to stop that gamma radiation from getting to you, because it's just energetic light waves in the end. That's how the energy is being transferred, is through light particles. Light as in the stuff that we see coming from the sun in the sky, right? Not as in something that is not heavy. So light as in the visual thing, not the mass idea. So light particles as in light waves. So it has a high level of penetrating power. But even though it's high energy, it's just energy. It doesn't have a charge to it, so it's less likely to ionize these living cells. It has a low level of ionizing power. It has the least level of ionizing power out of the three types we have talked about here. So alpha particles are really, really big, have a high level of ionizing power. Beta radiation, those electrons, they're much smaller, so they can get to you much easier. However, they can't ionize as well as the alpha, and the gamma is kind of the opposite of the alpha. So it's so small that it's getting to you all the time. It's much harder to stop and block it from happening. However, it can't do as much to you in the end. So again, it's a game of numbers, and in the end, we find gamma radiation. It is very dangerous to us because we can be exposed to so much of it, and it's much harder to stop. So it's just a game of, if you're bombarded with gamma radiation, you have that chance of things being ionized more often, even though it has a lower level of ionizing power. So here's a table to kind of summarize what I was saying, to give you a little bit of a more straightforward idea about these radioactive particles here. So if we have an alpha particle being emitted, that means we have a high level of ionizing power and a low level of penetrating power. Remember, it's the biggest of the three. However, it does have the greatest chance of affecting you. So beta radiation is kind of here in the middle. It has a moderate level of ionizing power. It can ionize, but it's not got the most ionizing power, and it's in the middle in size too. So it's much smaller than 2 protons, 2 neutrons. However, it is still bigger than something that has no mass, because it does have mass in the end, right? So it's kind of in the middle on both scales, and the gamma particles here have a low level of ionizing power, as they're not charged particles. They're a wave of energy. However, they have a high level of penetrating power because they are the smallest of the three. So again, what I want you to take away from this is that there are different kinds of radioactive particles that can be emitted from a radioactive atom. It's not always the same. They have different levels of affecting you in the end. Again, I don't expect you to memorize the high level, low level, penetrating power, ionizing power, but I do expect you to know that ionizing power is the ability to ionize atoms and molecules within living cells. And penetrating power is how easily it can get through certain substances to affect you. So that's kind of what I expect you to know about radiation and radioactivity. So let's talk a little bit about how we interact with this in our everyday lives. So I'm going to give you a couple of different definitions here about different kinds of nuclear reactions. So nuclear fission. Nuclear fission occurs if we kind of bombard a unstable nucleus with more neutrons. We can cause that nucleus to create a chain reaction of breaking into smaller and smaller nuclei while emitting radiation and a ton of heat. So fission is breaking apart of larger nuclei into smaller nuclei in the end. So if you have one big nucleus, you break it apart into at least 2 things, you've got fission going on. So this is actually what powered the atomic bombs, or A-bombs, that we created. So the Manhattan Project was the first experiment to actually leverage this idea that we could break apart nuclei, causing an extreme release of energy, right? So these were the people that studied and discovered that we could build these atomic bombs and tested to see how dangerous they could be. Fun fact, the first amount of radioactive uranium to actually be isolated apart from its raw ore was actually isolated at Iowa State in a stairwell in their chemistry building. You're actually not allowed to use the stairwell. They have concrete blocking off the stairwell, and it's got like really thick doors and stuff. Because that stairwell is still giving off radiation. So to be able to separate it, they had to basically put it through a filter, and we call those filters that they used in chemistry columns. And so, you know, I've used columns in my classes before, maybe about this big or about, you know, maybe a foot and a half tall, right? This one, they had to have it so large to actually be able to isolate these different isotopes and to actually separate out the uranium they were looking for. They had to have it basically in their stairwell so it could span all the floors of their chemistry building. I can't remember, I think it's like a 4 or 5 story building. So they had to have a column that was that tall to be able to complete the chemistry they needed to complete, right? So they had to put it in the stairwell so that they could do this in the end. So again, there's concrete blocking off the stairwell. There's other stairwells you can use, but it's kind of cool. It's the main one in front of the front doors and stuff like that. So it's pretty cool that was kind of done in a scenario, or kind of in a local-ish area, a school we may have heard of, know about. And actually, there was a 3 in 1 million chance that when detonating the first nuclear bombs in tests, that the power and energy from these bombs would ignite the whole atmosphere. We weren't quite sure that if we detonated an atomic bomb, it wouldn't just light the atmosphere on fire, poof, done, gone with life on Earth, gone with humanity, Earth's atmosphere, donezo. So I think that's an extreme risk that those scientists took when they actually chose to detonate the first nuclear bomb. But they took the risk, they moved the planet into the atomic age, and we were able to learn and study about these different things in different ways, and how we can actually use fission in a more useful manner rather than just a destructive manner in the end. So, I don't know, you've got a way better chance there of igniting the atmosphere than winning the lottery. You know, my family and I will buy scratch tickets, we'll play the lottery every now and again, so I like my odds better there than I do. I'd rather not ignite the atmosphere on fire. So, kind of a forewarning sometimes that scientists are out there taking risks that may not that you may not have chosen to take in the end. So, just kind of an interesting thought that could have happened. So, where else do we use fission in the end? So, fission is actually what drives nuclear reactors. So you have fuel rods of unstable uranium. They're placed down in water under a ton of concrete and lead shielding. So this is what it looks like to look top down at a nuclear reactor. All those different little circles that you see are the actual fuel rods themselves. And so once we kind of set the fuel rods into the reactor, they are bombarded with those nuclei to create neutrons to create a chain reaction of nuclei breaking down. So this gives off a ton of heat and energy. So the water helps do some of the shielding as well. It's actually the water in the concrete that actually helps a lot of the radioactive shielding. However, that water gets super, super hot. So the water is heated by the reactor going off, and it will heat that water. That water is then pumped through a turbine so that the turbine spins, and it produces electricity when this turbine spins. The water ends up cooling down, we cool it, we take it back through the system, the cycle starts anew. So when I was working at my internship at the Quad Cities Nuclear Generating Station, that's this guy here, they have 2 different reactors, and my job was to make sure that the water running through the reactor and the water running through all the systems was as pure as possible. So we were testing to see how much electricity our water conducted all the time, because we knew that if it was conducting electricity, it had some sort of contaminant in it. So there were certain levels where we could leave our water conducting a little bit of electricity. But one of my summer projects was to determine why we had so much sulfates in the water, because remember, sulfates are polyatomic ions. And so they were in the water, they were causing us to have a bit more electricity pass through our water than what we expected. So that was one of the things I got to work on in the end, was to try to figure out where that was coming from along those lines. So that's pretty cool. And so the way this kind of works too is yearly they shut down each reactor, and then they'll pull out the old fuel rods that have been expensed, and they'll put new fuel rods back in it. Quad Cities usually does this in like March or April, and so they shut down a lot of their power production to be able to do this. They take the caps off the reactors and they put new fuel rods in and stuff like that. So it's a pretty cool situation, and I feel very lucky to have had this internship, and I hope that you guys feel lucky that we live close to a cleaner form of energy than fossil fuels, and we get a lot of our power from the Quad Cities generating station. Fun fact, the first nuclear reactor was actually in Chicago at the University of Chicago. So Enrico Fermi was the one there, he was the one that led to the atomic bombs. He also realized that you could channel these ideas in other ways. So when he was working at the University of Chicago, it was his team that created the first nuclear reactor. I've actually been to Chicago where the reactor was and stood there. At Quad, I have actually stood on top of the reactor through tons and tons and tons of concrete, but I've been on the refueling floor and stood kind of where that cap would be on top of that. So I think that's pretty cool too. And so the fun picture you see of me here is what it looks like inside. This is their practice control room. So they have an exact replica of the control room where they work in to change all the different factors that might be affecting the reactors in the end. There are 2 at Quad. What you see me doing here is pushing what we call the scram buttons. So if we need to, for some reason, emergency shut down the reactor, we dump a ton of boric acid into it. The boric acid is great at absorbing all of those radioactive particles to stop the reactor from happening. However, once this happens, there's no going back, there's no bringing the reactor back, and it's gonna cause like a lot of heat, a lot of meltdown. That's what they did in the end to try to stop some of the reactors at Fukushima and Chernobyl and stuff like that. So once you've done that, it's over, end game. It actually takes pushing 2 buttons at the exact same time to make that happen. Again, these are the fake buttons, but this is me scramming the reactor. And one last fun story is that they call it scramming the reactor. There's a story. It's a legend. I don't know how true this is in the end. It's probably not very true. But so the idea is when they were starting up that first nuclear reactor, reactors have what they call control rods. So in between all of the different fuel rods, there are control rods that you can slide up and down to start, or not start or stop, but control the reaction. So you might want to slow it down for a bit. Let's say the people of the Quad Cities in Illinois and the Chicago area aren't using a ton of power today. Well, we probably don't need to be producing as much power, so we can slow down our production and our generation by inserting these control rods that kind of absorb some of these radioactive particles and kind of slow down that chain reaction, because there's not as many particles hitting those nuclei to cause those nuclei to emit more particles in the end, right? Well, if it's a really, really hot day, everybody flips on their air conditioning, we're drawing lots of power, we can pull those control rods back out a bit so that we can cause more of those reactions to happen, heat it up, produce more power in the end. So those are called control rods. Well, the idea was when they started the first reactor, if they had a meltdown, they had literally a guy with an axe that was supposed to chop the ropes that were holding up these control rods. Again, it's ropes. That's why I don't think that would work. A lot of heat here. So however they had it set up, it was supposed to be this guy, and he was called the Security Control Rod Axeman. So that's scram. So those are why we call them the scram buttons. But, you know, we could also be saying, get the heck out, scram. Things are going, you know, stuff's hit the fan. We got to get out. So This is me, again, hitting the scram buttons. This is kind of relatively what the inside of the control room looks like. I mean, it is exactly what the inside of the control room looks like in the end, so it's really cool that we can live by such a resource and things like that. I do want to remind you that this is a cleaner energy than fossil fuels are, and scientists are constantly working on how to reuse and reprocess this waste so that we can kind of move this technology with us into the future and it can become a bit more viable than what it is. By those scientists, I mean it was me. That was one of the things I was studying in grad school. I figured we figured if we could model these atoms better, these heavy radioactive isotopes, we could see how they participated in certain kinds of chemical bonding. So then we could, in the end, pass that information along to the experimentalists and say, hey, I think if you did this kind of reaction, you might be able to separate out this kind of isotope. And then we could start to process that nuclear waste in a different manner and turn it into some more usable items and things like that. So, pretty cool. This is one of my areas of expertise that I like studying, so I don't know. I hope you guys enjoy it too. So it's kind of a really, really cool idea to think about. And again, we're really lucky to have access to this information and to be able to see how this can affect our daily lives and everything like that. So we talked a little bit about fission. So what's the opposite of fission in the end? Well, nuclear fusion is the combination of two lighter nuclei to create a larger one. So these reactions give off more energy than that of fission. I think it's about 1,000 times more powerful in certain cases. And so things like the sun and stars are powered by fusion. So the main fuel for the sun is hydrogen and helium. These are constantly being crushed together by the insane gravity of the sun, so that they form larger nuclei. Once the sun or star reaches too large of a nuclei, aka iron, the star signs its own death certificate. It begins the end of its life cycle. In the end, all nuclei are trending toward iron. And so if it's larger, it's trying to emit radiation to get down to iron size. And if it's smaller, they're trying to slam themselves back into each other so that they can become iron in the end. One theory for the end of the universe is that everything will just be iron atoms in the end. So one of the ideas out there. But again, this iron nucleus is what in the end will stop a star, and that's what begins the end of its life cycle. It's going to consume all of its fuel at that point. There's nothing else it's going to be able to start to slam together and stuff like that. So stars are powered by fusion. And think about the insane amount of heat the sun has to be giving off, just what you feel when you're standing on the surface of the earth and how hot it can get. Oh my God, imagine being on the surface of the sun or at any of the planets that are closer than that. So fusion really truly is an insane amount of power in the end. So scientists have been trying to work on creating fusion reactors, but there are currently too many technical challenges. We don't really have materials that can withstand the heat of fusion in a reactor, so it's not really even on the table as far as I understand right now. However, they do make for great science fiction. So here is my second Spider-Man reference of the day. In Spider-Man 2, the villain Dr. Octo, not that big of a comic fan, but here he's creating a sun, and you definitely could not be standing right there back behind your fusion reactor trying to power anything like that. You could definitely, it would not work like that. That dude would be donezo. The whole earth would be donezo at that point. Like, no way. No way. So they make for great science fiction, but it's not true science quite yet. There are theories that we could create these things eventually when we have the right materials called Dyson spheres, so we could surround a star with something that could take in the energy from the star and pass it on to us in a useful manner. I think that's a bit more realistic in the end than creating a fusion reactor, but hey, they're both science fiction at this point, so who knows. So We actually kind of made sort of a second generation atomic bomb by using the principle of fusion in the end. So this is what an actual hydrogen or H bomb is. So you first do a small fission reaction to create the insane heat and temperatures that you would need to be able to fuse hydrogen atoms together. And when that happens, it creates a bomb that's about 1,000 times more powerful than an atomic bomb is. So we used the atomic bombs, and we've seen the impact of how powerful those are. And so these are 1,000 times more powerful than what those would be. So big yikes. We would not want to be involved with that. So I'm hoping we kind of keep that technology out of actually kind of thinking about using things like that. So again, scientists oftentimes think about can I rather than should I sometimes. So I think this is one of those times. So, but again, we have been able to create fusion as human beings in some sort of manner, but we have to even do fission before we can make fusion happen, and we're only fusing hydrogen atoms together, and it's definitely not as much as what could be created to create a sustainable fusion reactor in the end. So I think we're sticking with fission reactors for right now. So how else do we experience radiation? Well, you may be thinking, medicine. So yeah, we do use a lot of radiation in medicine. I'm going to talk about two different ways that we use it here. However, there are other kinds of radiation used in other forms as well, but these kind of involve the kinds of radiation we've been talking about in this class. We might do something called isotope scanning. So we might take certain types of cells will take up different kinds of radiation or different kinds of isotope, causing them to become certain kinds of hotspots on scans. So you can kind of see a scan of a person here. You can kind of see all of the different places those particles have been taken up. So depending upon what the doctors are looking for, they inject a certain kind of isotope into the patient's system in small amounts. This can be used to diagnose things like appendicitis, cancers, thyroid disorders. It can be used to do scans of internal organs. They'll choose a specific isotope that will be taken up potentially by, let's say they're looking for a tumor, and they know that this type of tumor that they're looking for really, really, really will accept a certain isotope into its system. What it'll look like is a bright spot on the scan in the end where you're like, holy crap, you do have a tumor. It's there, boom, because those living cells took in and processed those different kinds of isotopes, and we can measure the radiation coming off those isotopes in the scan, and that's how we know what's going on. So these radioactive isotopes become concentrated around the part of the body in question, or maybe they don't become concentrated if the scan's negative. And it can be interpreted to determine if there's something going on. And, this is why radiologists make a ton of money, is because they're able to determine how to administer these tests and how to read them in the end. So I think that's pretty cool that we can kind of inject isotopes in a relatively safe manner where we can put them into our body can process them, and while the body's processing them, we can learn a little bit more about what's going on internally as well. So pretty cool. The other place you may be thinking of is in cancer treatment, right? So radiotherapy. So radiation is particularly good at damaging rapidly dividing cells. So that is a main feature of cancer cells, is that they divide way more rapidly than any other kind of cell in your body. So doctors can aim gamma rays at the tumor from different angles to try to stop that division of cancer cells. So while the person can experience some negative side effects, oftentimes the good will outweigh the bad, and the doctors try their best to plan the treatment accordingly so that it will help the patient rather than hurt them. But either fortunately or unfortunately, even though we're shooting gamma rays at someone, it doesn't make them Hulk out. So still no superpowers from the radiation. We can always dream, right? But again, radiation is used in many, many other ways in medicine, and these are just two different ways you may have experienced them. So, this is bananas, BS, ANANAS. So oftentimes we are just experiencing radiation in our everyday lives from the things around us as well, right? So technology and other modern conveniences often give off small amounts of radiation that are considered to be harmless, not really affecting you. Again, we've talked about these different ways that they have different levels of ionizing power, different levels of penetrating power. So the kinds of radiation that are generally given off around us are considered to be harmless based upon these factors. There are, more than that, there are just radioactive isotopes that just naturally occur, right? All of this stuff is naturally occurring. We've just isolated it from our environment to use it in these other specific ways I've talked about. However, the land around us also contains those radioactive isotopes. So the land is constantly those radioactive isotopes are constantly changing and giving off that radiation. So here's a map of different levels of radon, radon being a radioactive atom, will give off radiation. So all of these different places in the United States experience just different levels of radon levels and radiation levels. So again, those are just things that are constantly changing around us. A lot of times humans have really adapted and it doesn't totally affect us all the time. If radiation affected us that bad, we wouldn't even be able to go outside. We wouldn't have evolved as a species. We wouldn't be here today even having this conversation if we hadn't evolved to kind of adapt to certain kinds of radiation. So even though it might seem a little bit scary when we're talking about some of these things, again, humans are resilient, we've been resilient, and we've gotten to this point, so there's at least that, right? And two, a lot of the space around Chernobyl, now that it's an exclusion zone and humans aren't living there to cause problems, for the animals of the area, I should say, they're able to kind of avoid a lot of the radioactive hotspots, and there has been a huge resurgence of animal life in the exclusion zone. So oftentimes, as long as they're staying away from the hotspots, they can live their life like they normally would, and they can live it a bit more freely than they might in other areas where they might be trying to stay away from humans and stuff like that. They've actually reintroduced a horse population there that was on danger of going extinct, and it's seen a huge resurgence being able to stay away from humans there. So I think that's pretty cool as well. So as long as they're staying away from a lot of those hot spots, it's probably not affecting them enough for it to matter. And they've kind of, once they lived through the initial shock of everything, they've been able to rebuild their population. So yes, we should stay away from high levels of radiation, but in some ways it's going to be harmless to us. And bananas. So bananas are kind of one of the kind of kitschy little fun famous things that are radioactive. So potassium, one of the main features of bananas, actually occurs relatively often as its radioactive isotope. So bananas have a small amount of radiation in them and can go off a small amount of radiation. So if you've eaten a banana, you've eaten radiation likely in the end. So my intern friends and I, when we worked at the nuclear power plant, we would often compare our daily radiation doses to like how many bananas we would eat. On average, I was in the plant the most out of them because they were working as engineers and I was working as a chemist. They might go verify a drawing, but I had to go take readings on different instruments and stuff like that, so I was spending a bit more time in the plant. I rarely got up to half a banana. There was one day where I was doing some tours and I had to take my readings, and I went into a different area that time that was a bit more hot-spotted, and I think the most I ever even got close to was 2 bananas. So even working in the nuclear power plant, inside the actual buildings, it wasn't even exposing me to more radiation than I might have been getting by eating a banana every day or something like that. So there is an official unit called the banana in radiation. We don't use it actually 9 times out of 10 as scientists, only if you're goofy interns having fun thinking about radiation as bananas. And I mean, there are more dangerous places in the plant. However, a lot of times if we're going to do that, we're going to send robots or we're going to use extremely special equipment to be able to access those areas, and they're only accessed when extremely necessary and needed, and people are going through protocols. So even though again it might seem scary, it really isn't in the end, and you're really, the way we've built the plant, you're not even experiencing that much radiation. Like I said, My maximum, I think, was about 2 bananas one day. So have a banana, everyone. Experience your radiation for the day. And I'll talk to you a little bit more about how this radiation occurs, what it means, how we can use it for certain kinds of measurement in part 2.